Hello, my name is Joshua Zoe, and I'm presenting my term project for classical molecular materials modeling on anisotropic particle simulations. So, what are anisotropic particles? In traditional atomic simulations, we typically use a point sphere model, and these simulate each atom and particle as a sphere that is volumeless and isotropic, which means it's uniform all around. This makes calculations very straightforward, as distances can simply be a distance between 2 points. Now, this is very good for atomic simulations and some coarse-grained simulations where we can approximate everything to be a sphere. Now, anisotropic particles take away this assumption that a particle is spherical in nature. And so this means that any shape, so an ellipsoid, a dodecahedron, a cube, anything can be modeled with an anisotropic particle. And this is especially useful for doing larger particles like nanoparticles or more complex systems like liquid crystals because it allows for the relaxed assumption that everything can be simplified down to a point. Now, why anisotropic particles are not really used more is because they have a lot of added complexity to them. First off, there's a lot more degrees of freedom for since each particle now, alongside translational degrees of freedom, now has rotational degrees of freedom. Additionally, since there's now a concept of volume in Monte Carlo simulations or molecular dynamics simulations, there's always a possibility that a particle could end up in another particle, and in Monte Carlo, you could typically reject this, but in molecular dynamics, this will present an issue with excessive forces if the step size is too large and particles end up clipping into each other. And lastly, particle-particle distances become really expensive since now we have to consider points across the surface, not just one point per particle. And additionally, for concave particles, then there's raises a question that there are multiple points that are equally close to between particles, resulting in much more complicated calculations needed to determine how forces should act on each other. And like I said, forces and virial expressions may not be well defined for certain particle shapes, especially concave shapes. So we can implement anisotropic particles by placing some restrictions on these. First off, we're going to assume that all the particles we are interested in simulating are going to be convex. And that means that each shape is going to be a kind of regular shape that we may be familiar with. In 2D, this would be a hexagon or an octagon or a square, triangle, these sorts of shapes. And this allows us to assume that the interaction between any two particles can be dominated by one vector, the closest distance between the two particles. Secondly, we'll assume that all these particles are centered about their point of rotation, or in other words, their center of mass. We could, in theory, have very elongated particles, but once, but if without assuming that particles are centered on their center of mass, then calculating angular momentums and rotation becomes much more difficult and expensive. We'll also assume that particles are evenly distributed, and so this that way force calculations can really approximate these particles, can still use a point approximation to emulate the masses of each particle. And lastly, we're going to assume that a particle's surface can be expressed by a combination of equations in spherical coordinates. Now, this is not a typical assumption for anisotropic particles, but it is one that I am going to implement for the convenience of calculating, determining distances between particles. And so we'll need a coordinate systems to use. And this will be largely unchanged to isotropic particle simulations. The system coordinates will be in Cartesian coordinates. So each kind of particle, we can use the XYZ position to describe the center of each particle. But to describe the surface of a particle, we'll be using spherical coordinates. And this will so for each particle, there'll be a local psi and phi angle that we can then use to describe. And the reason I chose a spherical coordinate system is since the simplest anisotropic particle is an isotropic particle. It's a sphere. And this makes kind of building upon these layers, either cutting planes into this particle or just adding on different functions to them, uh, a bit more straightforward. And now, kind of like what I said, we'll need to treat the distances between particles more explicitly compared to isotropic particle simulations. And we'll have two distances between any two given particles. One will be the center to center distance, and we'll use r to denote that, as well as the closest distance between any two particles, and that will be r subscript c. From R, since we have analytic functions for each of these surfaces, we know what the points P1 and P2 are, and we can describe them as a function of theta and phi. Through the close through an optimization between these 2 points, we can then determine what the closest distance is for any two given particles, so long that they are concave and we have analytical functions for their surfaces. With these two distances in hand now, we can then proceed to calculate energies and subsequently forces. With this paper here uses these two expressions to express the potential energy of a system of anisotropic particles. It's really just going to be a correction on top of the center-center isotropic potential energy. And this correction term will need two additional parameters that can be specified depending on what system we're interested in. So, the work I've done so far is setting up a way to create these anisotropic particles. And like I've described before, we'll use a series of uh, expressions, in this case, one surface defined by a couple of planes to cut into the sphere. And this way we can create a particle, and which this is shown on the right. For the images on the right, I sampled like several points along all the surfaces. So each of the little spheres you see, like the small spheres you see, are kind of representing points on the surface. And this kind of really shows that these set of expressions can be used to express a cubical particle. Similarly, you can create a cylinder. And since both a cylinder and a sphere have well-defined functions in spherical coordinates, this is quite straightforward. And then it's just a matter of cutting the lengths with additional planes in the z direction. Now, after making and defining a particle, I'll need to incorporate a rotation, since this is something that we did not need to consider in the molecular dynamics and Monte Carlo we've created during this course. So the way I did this is that each particle can store its orientation as a 3x3 rotation matrix. And each time a particle, if we want to rotate a particle, we can just provide it an axis and the degree of its rotation. Then we can continuously update this rotation matrix during the process of simulation. And I used for this Rodriguez's rotation formula, which is a general uh, way of creating a rotation matrix for a given axis and angle. And due to the properties of rotation matrices, these matrices can be continuously applied on top of each other and cumulatively store the total rotation that a system has gone through. And lastly, I set up the code and optimization such that the distance between two particles, the closest distance, can be readily calculated. So here on the screen, I have two spheres, and as I rotate them around, the green arrow points in the closest point-to-point distance between these cubes. And as you can see, the current implementation works at least quite reliably for the cubes, and it works also quite reliably for cylinders and any other particles I've implemented so far. And so now that I have these particle-particle